Hello everyone, welcome to this session on daylight strategies and techniques part 2. Before we get into the details of the strategies and these techniques, let us understand the solar spectrum. Here you see the solar spectrum. You see that it consists of three main regions: the ultraviolet region, the visible region, and the near infrared region. And if you pay attention, you will see that this graph shows you the energy distribution in these three regions. So the ultraviolet region consists of 6.6% of the total energy that the solar radiation brings in. The visible part of this spectrum consists of 44.7% energy, and the near infrared region constitutes 48.7% of the total solar energy that is falling onto a building. Now our interest is to bring in as much visible part of the spectrum as possible and to stop all the ultraviolet and near infrared part of the spectrum, because that doesn't aid in vision. And in the places like in tropics, where most of the time of the year we are doing cooling, we don't want this radiation to enter, because that will only increase our air conditioning load. So our ideal glass will be the one which allows all the visible part of the spectrum to come inside and doesn't allow the ultraviolet and the infrared part of the spectrum. This is our ideal glass. But in reality, there is nothing like ideal glass. In real life, we have glasses which have some transmittance in all the wavelengths. So let us try to understand how does the glass behave when the solar radiation falls on it. So when the solar radiation falls on the glass, three things can happen. Some of the radiation can pass through the glass. Some of the radiation can be reflected from the glass. And there would be some which will be absorbed by the glass. There are only three possibilities. Now, the radiation that has been transmitted through the glass comes into the space. The radiation that has been reflected from the glass remains outside. The radiation that has been absorbed by the glass, it raises the temperature of the glass. And then this energy is dissipated by the glass in the form of long wave. Now this long wave, some part of this long wave can come inside the space and some part of this long wave can go outside. So in totality, if you see, when you are looking from inside, you are getting infrared radiation directly transmitted, you are getting visible radiation directly transmitted, a little bit of ultraviolet radiation directly transmitted, and the radiation which is being absorbed being re-emitted as long wave radiation. So if we want to see the glass properties, especially from the point of view of daylighting, we are interested in visual light transmittance. However, we just can't look glass from the visual light transmittance point of view. We have to also see how much energy it brings in. And for that, there are two properties. One is solar heat gain coefficient and the another one is U-value. We will understand all these three and then we will proceed further. What is visible light transmittance? Visible light transmittance is the amount of light in the visible portion of the spectrum that passes through the glazing material. So suppose there are X units of visible light that is falling onto the glass and X by 2 passes through, then we can say that 50% is the visible light transmittance of the glass. Higher the VLT, it is good for daylighting because we will get more illumination indoors and we will be able to save on the artificial electrical light energy consumption. Visible light transmittance is influenced by the glazing type, the type of coating, number of panes, etc. Generally, for a regular glass, we will see visible light transmittance of the order of 80 to 90%, and for a heavily tinted glass, we might get it down to as low as around 10%. Typically, we would be expecting this value to be around 50 to 70% in the buildings where the glazing areas are small, and if you have large glazing areas, then you would like to keep it low, around 20 to 30%. Now let us look at solar heat gain coefficient. Solar heat gain coefficient is the measure of total solar energy that is transmitted through the glazing into the building. So it is basically a number between 0 and 1. Lower the number, that means lower amount of solar energy is being transmitted. Higher number means more amount of solar energy is being transmitted. We will like to keep this number as small as possible. Just like visual light transmittance, the solar heat gain coefficient property of the glass also varies with the type of coating, number of panes, etc. Therefore, when we are selecting the glass, we should look at how we can get low solar heat gain coefficient and high visual transmittance. Generally, for clear glass, we can get solar heat gain coefficient around 80%. In high performance buildings, we would like to target the solar heat gain coefficient around 20%. Now these two properties are very important because they tell us how much light the glass will bring in and how much energy it will bring in through direct solar transmittance. We can combine these two values into one value and we can call it light to solar gain ratio, LSG ratio. This is nothing but VLT divided by SHGC. So suppose a glass is having 50% visual light transmittance, therefore the VLT will be 0.5, and if the solar heat gain coefficient is 30%, then SHGC would be 0.3, then the LSG ratio will be 0.5 divided by 0.3. Higher the LSG ratio, better it is because it is bringing in more light for lesser amount of heat gain through direct solar radiation. Let us now look at what will be the ratio for our ideal glass. In case of ideal glass, we said that it allows 100% visible light to come in. Therefore, the VLT of the ideal glass would be 1. We also saw that visible component of the solar spectrum consists of 44.7% of the total energy. Therefore, 44.7% of the energy will get transmitted through the glass. Therefore, the SHGC of the glass would be 0.447. Hence, LSG of the glass would be 1 divided by 0.447, which is equal to 2.22. So this is the LSG of the ideal glass. Usually in real life, we will not get glass which will have LSG hitting so high. What does real life glass look like? So if you see this graph which shows on the x-axis visual transmittance and on the y-axis SHGC, you will see that normal glass, which is not spectrally selective or tinted, would generally have SHGC and VLT of the similar order, and they will lie on this line. If you have a glass which is tinted or which is reflective in nature, you will see that these glasses are towards the higher end of the shading coefficient, the solar heat gain coefficient. They will have higher SHGC and lower VLT. These are the glasses that we would like to avoid in buildings because they don't bring in light, they bring less light and they bring more heat. The glasses that we would be interested in would be on the lower side of the this line, and they will have higher visual transmittance and lower solar heat gain coefficient. So they can have this ratio around 1.5, 1.7, 1.8 likewise. You will also see that there is a limit below which you cannot find any glass because of the obvious reason that if the glass has a high VLT, it will have at least some minimum SHGC corresponding to the energy that the visual light brings it with itself, right? So you cannot have a glass below this theoretical limit. Now let us look at U value. So U value indicates the rate of heat flow due to conduction as a result of temperature difference between inside and outside. This is different than SHGC. Here the heat is getting transferred by virtue of conduction because of the difference in the temperature between inside and outside. Normally, in case of summers, outside will be hotter than inside, and therefore heat will be flowing from outside to inside, and this will be measured, the U value will be measured in the units watts per meter square Kelvin. We would like to have lower U value so that we get less heat conducted into the building. Again, the U value depends on the number of panes, the type of gas that is filled inside the 2 panes, and other factors. Lower the U value, more insulating is the glass pane or the glass assembly. So what is a high performance glass? A high performance glass for us, that is in the tropical regions, would be the one which reduces the heat ingress and at the same time allows a lot of light to come in. That means it should have high visual light transmittance, it should have low solar heat gain coefficient, and it should also have low U value. A typical high performance glass would have value of solar heat gain coefficient of about 0.2, 0.25, U value of about 1.7, and visual light transmittance of about 40%. Now we have understood the glass and we have understood the solar spectrum. Now let us see how we can enhance the performance of our windows.